Okay, hi guys. So in this lecture, we'll be seeing fulfilled and half-filled theory, or rather, the exceptions which we see in case of electronic configurations. Okay, so let's get started. So we'll be seeing fulfilled and half-filled theory. Okay, so these are more or less of exceptions. So for chromium, we have the configuration as argon 10, or rather argon 18, and then we would be having 3d4 and 4s1. Okay, this is the configuration of argon. And then actually what happens is, as 3d5 would be more stable, this is 4s2, as 3d5 would be more stable, hence one of the electrons from 4s actually transfers itself from s orbital to d orbital, as here we get a half filled d orbital. So d orbital with 5 electrons is more stable than d orbital with 4 electrons, as it gets half filled. This is more stable than this one. Okay, then let's see the case of copper. So copper 29, again we'd be having configuration like argon 4s1 3d10. Okay, so one of the electrons would be getting transferred from 4s to 3d. Then again we have MO42. Again we would have rather crypt uh, KR would come here with 36. Okay, and then we would be having 5s1 and 4d5. Again one of the electrons would be getting shifted to here, which it was initially 5s2 and 4d4. With this, again we would be having something like XC54, 6s2, 4f14 and 5d4. Okay, so this will actually convert itself into this 6s2 electron will go into 5d4 orbital to convert 5d into 5d5. So as a result, we would be getting 4f14, then 5d5 and 6s1. Okay, so d block elements have electronic configurations like d block elements have electronic configurations like n-1d 1 to 10, then ns 1 or 2. Okay, but due to low n-1 electron participation in the bonding difference, due to low n-1 electron participate in bonding, the difference in ns and n-1d orbitals gets lesser. Okay, so as a result, one of the electrons gets transferred to d orbital as and when required due to the partially filled and half filled rule. So whenever there is a deficiency of only one electron in complete filling or half filling of a subshell, then to gain extra stability, one of the electrons from the nearmost subshell, as we already saw in the previous statement, that these two has very less difference in energy. Okay, so let me rewrite it, or rather let me write it. So n minus 1d and ns have less difference in bond energy, or rather simply energy. Hence, whenever there is a deficiency of only one electron in complete filling, and half filling of a subshell, then to gain extra stability, one of the electrons from one electron from nearmost subshell, in our case it would be n minus 1d, or rather ns shifting to n minus 1d. So nearest subshell in our case would be ns of higher energy level comes to DNF subshell of inner shell of lower energy level. Okay, so next we'll be seeing that, or one more note, that full filled and half filled rule is not applicable for S and P block elements due to absence of electron at higher energy level. Okay, so full filled and half filled rule is not applicable for S and P block elements due to absence of electron at higher energy level. Okay, so next we'll be seeing the cause of stability of full-filled and half-filled configuration of subshell. Okay, so we'll be seeing now cause of stability of full-filled and half-filled electronic configurations. Okay, so full-filled and half-filled configurations of a subshell are extra stable than any partially filled configuration due to the two following reasons. One is higher aggregate value of exchange energy and pairing energy, and second one is symmetrical or equal distribution of charge of electron density along xyz direction. Okay, so reason is first, higher aggregate value of exchange energy, and pairing energy. Next is symmetrical or equal distribution of charge of electron density along x, y and z direction. Okay, so we'll be seeing more into the exchange energy and the pairing energy in the next lecture. So till then, good luck and goodbye.